Okay, guys, let's continue our discussion on the creative provisions concerning the unified provisions of the ACI code. So let's now compare the old provision before 2002 and the newer provisions after 2002 regarding the limits. Okay, in terms of the parameters they use, we will try to make some comparisons on the factors we need to know, no? For us to have a feel of what and how the activity will be achieved concerning the strain limit. So for the tension controlled strain limit of 0.005, which is the upper limit, uh, this corresponds to the ductility requirement imposed by the 2002 code on flexural members. And how do they match in terms of the balance condition? Remember what I said in my previous lecture, that your epsilon balance is simply the point at which your steel will yield. Okay, your extremmost tension steel here will have an epsilon y simultaneously when your concrete crushes in compression. So your balance, okay, your balance definition is actually exactly the yield uh, behavior of your steel here. So this epsilon y gives you the balance condition as far as your strain steel is concerned, and this also gives you the location of the neutral axis at the balance condition. So how do we therefore get the minimum, not the maximum? So there are some corrections here. The minimum epsilon such that the tension controlled strain limit will be defined. So we simply make use of a ratio and proportion here. Of course, we are referring here at the level upon which your depth here is defined by the extremmost uh, tensile reinforcement PT, not the effective depth of T. Okay, so DT can actually be approximated by around 1.08 of your effective depth. Okay, you can use other factors if you want. You can use exact values if you want, but for the sake of simplifying the discussion and the computation, you might as well use this as your parameters. Okay, so if I want to get now the minimum, which is a point 0.005 as your upper limit, so I will be making use of a ratio, simple ratio of 0.005 and your epsilon balance or epsilon yield. Okay, so this epsilon yield is equal to Fy over Us. So for grade 40, if you want to compute it, you will get 2.38 of epsilon balance. And if you want to get the minimum steel strain that we need for this limit to be uh, satisfied, then we can simply divide grade 60 over your modulus of elasticity gives you this ratio. Okay, so again, I'm sorry for the error in the computation here. So the above ratio is ideal for serviceability aspect of design and solves the problem of bar congestion and conforms well to seismic provisions. Okay? So the net tensile strain limit of 0.004 on the other hand, which is actually 0.00376, corresponds to the previous code version of Romax is equal to 0.75, right? So in your problems that I'm going to ask you to verify this. Okay, and verify this also. Some computations or derivations I will be asking you to verify later. Okay, for the 2002 code, the following equations may be noted. No? So if we are going to convert your parameter CV in terms of CTC, where CTC, the tension control, is defined by this epsilon TC 0.005 as provided for in the ACI code provision. So this corresponds not on the Emacs, but rather then a correction, the E minimum on the previous codes. Okay. So for rectangular sections, I already discussed to you how to incorporate equilibrium conditions, no, with the compatibility of strain. So this is simply T is equal to C. Okay. So we can derive the ratio between your raw TC by defining raw TC as your ASTC all over BD and making use of a proportion here for CTC is equal to 3/8 of your DT. So again, if I have here the diagram, so this is my CTC, this is 0.003, and I have 0.005. So the ratio of this triangle is simply 3/8. Okay, so this is the ratio. 3/8 of the effective depth from here to here is your DT. Again, DT is the extreme tensile steel, not the effective depth. But if we can come up with an exact computation, if the problem is already there, or we can approximate it if the given values is still unknown. Okay, so by proper manipulation on this and recalling our previous code for raw B, we can now make use of an expression in terms of raw TC and raw B by simply dividing raw B or raw TC here with that of raw B here. Okay, so dividing the two, we will get this. Beta 1 will cancel, beta 1 over m will cancel, so we get this. And some manipulations on the value of dt over d. Okay, so by assuming layering of bars, let's say 2 layers, etc., we can come up with an average ratio of dt and d 1.08. Okay, and if we get the average and substitute it here, we can relate raw TC and raw V in terms of this. So in our new version, in our 2002 and the newer version, the maximum steel ratio is slightly lower, but compares fairly well with that of grade 60. Okay, because this is 0.75 actually on the older codes. Okay, so for the newer code, it's a little bit lower because of some rounding off of numbers, but this actually shows us that there has been no uh, drastic change, but rather a more flexible uh, way of achieving ductility was just given because of the range at which your compression member and your flexural member is treated. No? In the unified provision, there is what you call a transition zone in which The inclusion of your reduction factor or the factor of safety there may contribute uh, fairly in the in achieving a conservative design, but a ductile behavior is ensured. Okay, so that's it for the comparison. So I'll see you in the next video to discuss to you some highlights on strength reduction factors, uh, comparing one from the other. So the older codes are here for us to understand them para mas maintindihan natin yung reason why we keep on revising, no, the factors in the newer edition of the ACI, the NSAP codes. Thank you very much for listening. I'll see you in the next video.